Hey there, science fans! Have you ever wondered what holds the atoms in a grain of salt together? The answer is ionic bonding. It's like a chemical glue that keeps oppositely charged ions stuck together. Atoms are always trying to have a full outer shell of electrons. It's like their version of having a tidy room. Some atoms, like those on the left side of the periodic table, have extra electrons they want to get rid of. Other atoms, like those on the right side, need a few more electrons to fill their outer shells. This is where ionic bonding comes in. Atoms with extra electrons, like sodium, can give those electrons to atoms that need them, like chlorine. When this happens, the sodium atom becomes positively charged, and the chlorine atom becomes negatively charged. These opposite charges attract each other, forming a strong bond called an ionic bond. This is what holds the sodium and chlorine ions together in a crystal of table salt. Now you might be wondering how many electrons an atom wants to gain or lose. That's where valency comes in. Valency is like an atom's combining power. It tells us how many electrons an atom wants to gain, lose, or share to have a full outer shell. For example, sodium has 1 electron in its outer shell. It wants to lose this electron to have a full outer shell like the noble gas neon. So, the valency of sodium is 1. Chlorine, on the other hand, has 7 electrons in its outer shell. It wants to gain 1 electron to have a full outer shell like argon, so the valency of chlorine is also 1. Common ions are formed when atoms gain or lose electrons to achieve a full outer shell. For example, sodium commonly forms a sodium ion, while chlorine commonly forms a chloride ion. These ions are important because they are the building blocks of ionic compounds. So far we've talked about ions formed from single atoms. But did you know that a group of atoms can also act like one big ion? These are called polyatomic ions. A polyatomic ion is a group of atoms that are covalently bonded together and have a net electric charge. One example is the sulfate ion. It has 1 sulfur atom and 4 oxygen atoms bonded together, and the whole group has a charge of -2. Another example is the hydroxide ion. It has 1 oxygen atom and 1 hydrogen atom bonded together with a charge of -1. Polyatomic ions are important because they often make up parts of ionic compounds. Section 4. Formation and properties of ionic compounds. Ionic compounds are formed when oppositely charged ions attract each other and form a crystal lattice structure. This structure is like a repeating pattern of positive and negative ions held together by strong electrostatic forces. Ionic compounds have some unique properties because of their strong ionic bonds. For example, they have high melting and boiling points because it takes a lot of energy to break the strong bonds between the ions. They are also usually soluble in water, meaning they dissolve in water to form a solution. When dissolved in water or melted, ionic compounds can conduct electricity. This is because the ions are free to move around and carry the electric current. Section 5. Naming ionic compounds. A system for identification. Chemists have a special system for naming ionic compounds. The name of the metal ion comes first, followed by the name of the non-metal ion. If the non-metal is an element, its name changes to end in ID. For example, Nasyl is called sodium chloride. If the compound contains a polyatomic ion, the name of the polyatomic ion is used. For example, Na2SO4 is called sodium sulfate. This system helps scientists quickly identify and communicate about different ionic compounds. Section 6. Real-world applications. From salt to batteries. Ionic compounds are all around us. We've already talked about table salt, which is essential for cooking and flavoring food. But did you know that ionic compounds are also used in batteries? Batteries store chemical energy and convert it into electrical energy. Many batteries, like lithium-ion batteries, rely on the movement of ions to function. In a lithium-ion battery, lithium ions move from the negative electrode to the positive electrode through an electrolyte, which is a material that conducts ions. This movement of ions creates an electrical current that can power our devices. As the battery discharges, lithium ions move from the negative electrode to the positive electrode. When the battery is charged, the lithium ions move back to the negative electrode. Section 7. Conclusion: Ionic bonds in our everyday lives. From the salt we sprinkle on our food to the batteries that power our devices, ionic bonds play a crucial role in our everyday lives. Understanding how ionic bonds work helps us appreciate the chemistry that makes our world tick. By learning about valency, common ions, polyatomic ions, and the properties of ionic compounds, we gain a deeper understanding of the matter around us and how it interacts. So next time you pick up a grain of salt or charge your phone, remember the amazing world of ionic bonding that makes it all possible.